All right. Happy Tuesday. So welcome. So now we're doing chapter 24, starting redox reactions. And then we do have our midterm next week, so just kind of keeping an eye on things. I feel like the quarters just fly by. So just keep that.
So it's through 24, right?
Yeah, so this will be our last chapter on the midterm. And then we'll review on Tuesday like we normally do, test on Thursday, or whatever alternative arrangements need to happen for that. And so I think the syllabus is updated for what kind of our current plan is. So just looking at the lab. So we don't have lab officially next week for midterms, so that just allows for extra time and everything for accommodations, so we don't have to worry about that. And then this is a good week to make up anything if there's any stragglers on the phosphoric acid lab or anything else. And then we'll skip around and do the one pot, at least assuming that. So why we moved the one pot was also that people said that they were going to come like film and get action shots of you. I don't know if that's happening or not. I never got confirmation. So we'll see what happens if people show up on, it's supposed to be on the Tuesday, but again, I don't even know if that's happening. But that's why we kind of moved the one pot there. And then, of course, field trip next week. So we won't have lab on that Thursday, right? But another good makeup day if anything needed to happen. And then, right, we're not going to have class on Tuesday, so just the Oregon Caves. So, of course, make sure to get...
No class Thursday after the Caves.
Tuesday after the Caves. So we will have...
Caves on Thursday?
Caves is on a Tuesday. So May 12th is a Tuesday.
But then, what's going on that Thursday?
Just no lab on Thursday. Yeah.
Sorry.
So no lab Thursday. And so there won't be a quiz. We'll just take the 2 hours to lecture that week. Sorry, flipping back. So then, so 12. So then I think that's the 14th, right? No lab Thursday, May 14th. So caves. So obviously no class. And, right, obviously we're not going to meet in class. We're not going to have lab after the caves, obviously, right? So that's our class time for today, or for May 12th, is the caves. So make sure that you get your permission slip filled and returned if you haven't already done that. And then somebody asked about guests. So, yeah, just get me a name of any, guests if you want to bring mom, dad, significant other, brother, whatever. As long as they're obviously physically able to do the Oregon Caves, right? There's a lot of steps, but we've had grandmas in the past actually, so perfectly fine. Oh, question, yeah.
Are you gonna release a review or study guide for the midterm?
I did actually open up on Blackboard some old materials, so you have access to that. So yeah, I should have just opened up, and I just opened it up today. But there's our review folder, so then, yeah, you can poke around in there, and then of course we'll do the review on Tuesday, which will be representative. And then, yeah, exam is on Thursday, so we're going to review on Tuesday. Any other questions? So let's just jump into chapter 24 then, or let's see if we can recall what some redox reactions are, because I'm sure you guys know some redox reactions. And so these oxidation reduction reactions or redox reactions are just reactions in which electrons are transferred from one atom to another. And so can y'all think of some examples that we've seen of some redox reactions? What are typically redox reactions?
Combustion.
Yeah, so combustion's a good one.
And then like iron rusting.
Yeah, so now people are, so I heard zinc sulfate as well. The zinc sulfate and copper, right? So all those are, and then I heard the term single replacement, so good. So yeah, those are kind of our two big, right, case scenarios. It's either it's a combustion reaction or iron rusting is kind of a combination with just oxygen. So you could kind of think of it as somewhat a combustion. It's just not an organic combustion. So of course, combustion products, right, CO2 and water. Oops, sorry, trying to write H2O and water at the same time. Those are our products. Okay, good. So you guys, right, have already seen it in our year-long chemical journey, so you're kind of aware of it. Or we'll also put for single replacement, right, kind of anything in elemental form, kind of, right, going away or becoming something else. All right, so that's pretty good that you guys can already, again, identify them. And so then we'll just kind of formally make sure we go over our terms. And so we have atoms that lose electrons are being oxidized, and atoms that gain electrons are being reduced. And then I kind of encourage you to start seeing them, again, in terms of like their functions. So I kind of tease that with our sodium, right? So again, our sodium tends to lose an electron, so that's going to be also considered, right, our reducing agent. So other terms. And that's often how, like, the working chemist will think about these. Again, you're looking at a metal. Usually you're trying to reduce the metal's oxidation state to get it to do something cool. And so you'll be looking at these reducing agents to help you kind of do that transformation. So same thing with like chlorine or fluorine, bromine, all your halogens, right, are kind of considered your oxidizing agents. Remember, that's also kind of an additional hazard if you remember your symbols, right? We have first the flammable hazard. There's my horrible flame. But then we have the extra when you have fire plus O, so that's an oxidant, right? So then, again, that's just telling you that it's our oxidizing agent and typically gets reduced. So again, they want electrons. Again, just thinking about these typical elements that are your oxidizing agents, right? Fluorine, chlorine, bromine, they're all very electronegative. They all want electrons, so they favorably undergo this reduction process. And I think we're already kind of seeing this, or we already kind of know this, but just to emphasize the point, our oxidation reduction reactions have to be coupled, right? So we're obviously not going to have just an oxidation if there's no reduction. They work in pairs. And so again, just more either formal definitions or how to identify it. And so when something undergoes oxidation, so that is our process that occurs when our oxidation number increases. And again, we'll kind of go over how to identify that. And then it's going to be losing electrons. Typically we see it, especially right combustion examples, that our compound will add oxygen, so that's a good kind of red flag key. Or the compound loses hydrogen, and then of course you would have electrons as your product for your half reaction. And then reduction, So the opposite process, we can, right, compare. So now our oxidation number of our element decreases from, again, gaining electrons. Our element gains electrons, so there we have it. And then again, especially in combustion, we might see it losing hydrogen, or excuse me, I said that wrong, losing oxygen, gaining hydrogen. So once we add hydrogen, again, that's a good clue that we probably did a reduction. You'll kind of see that in organic chemistry too, the hydrogenation reaction. And then, of course, electrons as reactants. And then have you guys heard of like the mnemonics that kind of go along with these oxidation reductions? I don't know if people have their favorites. Yeah, so there's oil rig. So oil rig. So oxidation is losing electrons. Oh, let me give myself more space. Move down. I don't know why that's coupled. Reduction is gaining electrons. And then I have another one as well. Yeah.
Leo goes Gur.
Yeah, which what identity is Leo's? I've heard Leo the leopard is the one, but it could be Leo the tiger, so I was curious what cat
Leo has to be a lion.
Okay, so we all like Leo the lion. Well, I used to teach at a school where we were the leopards. Actually, it was Leo the leopard, so that's why he had an identity change there. But so yeah, losing electrons, oxidation, gaining electrons, reduction. I would draw a cute tiger, but I realize it won't come out correctly. But yeah, whatever your favorite fuzzy cat is. So yeah, those are two good ways to remember oxidation, reduction. And so again, like we're kind of starting to see, and we kind of were teasing this too last week with our activity series, right? You're kind of seeing, well, were things reactive or not? And some people mention either like confusion or discrepancies with the iron reactions. And well, part of that is that we weren't looking at our full half reaction. And so that's something that we'll do with our equations, is that we want to separate them into our half reaction. So we'll have our oxidation half with again our electrons as products, and then reduction has electrons as reactants, right, since they're being added. So then we could look at our reaction here. So 3 equivalents of chlorine gas plus our iodide in water gives us 6 equivalents of chloride plus iodate and our H plus or hydronium ions there. And so then you just separate, right, your two species. So we have our iodine, and then, so iodine going to iodate, right? So again, there's our addition of oxygen, so kind of our hint at what's going on, that it's being oxidized. And then separate out our other half. So chlorine, chlorine, and have to figure out where your water fits in. That doesn't change oxidation states, so that's useful for balancing. Then we see our reduction. So right, chlorine going to chloride. All right, so let's first, Sorry, I was looking for, where do we go over our oxidation number rules? I'm looking for that. Maybe this note version I have is not complete. Let me try something. Sorry, we don't have our rules on here. Sorry, let me pull some old notes where I think I have a copy of this. Blah, blah, blah. This is what I was missing. Just this little section here. There we go. All right, so before we get too deep in these redox reactions, we should go over how to assign our oxidation states again, in case we forgot. Slash, it's been a while, and right, it's kind of, we're doing half a refresher here. So let's see. No, I want a periodic table. Sorry, I'm trying to steal a periodic table from my other notes. There we go. So recall we have our oxidation states, which I didn't mean to copy, but that worked well. Right, so just go back through your periodic table, make sure you have your oxidation states there, or again, right, kind of clear the cobwebs. So kind of going back to first quarter and recalling back, okay, our alkali metals, we remember they like to be in the 1+ oxidation state. Again, typically, right, we're going to look at some exceptions. So let's go back to these notes. So, right, this tells us now our priority. So kind of putting back, again, our Gen Chem stuff with now. And so what I mean by priority is, okay, well, again, obviously we have our periodic table and what they tend to do. But then, again, now we're going to analyze our compound very specifically. And so that means that fluorine has priority, meaning it is always -1 for its oxidation state, right, when it's in a compound. And so, again, obviously, right, this is in a compound. So in the elemental form, right, it is 0 for oxidation state. So just, again, remember that, or write it down if we haven't already talked about it. Okay, so then elemental form is taken care of. And now in a compound, so like we said, fluorine is always -1. And then oxygen is 1. If you remember, we also usually based our compound off of, except, and it's in here in these notes. And so, of course, fluorine, right, we may have to analyze if there's something weird there, if there's like an oxygen-fluorine compound, so that would be an exception, right? But the other major exception is when it's in that peroxide. So remember, that's like hydrogen peroxide would be our simplest example of that. And you could quickly start to balance out your oxidation state. So it's easy to do in this little molecule. So, right, hydrogen's typically 1+, so 1+, 1+, so that gives us 2+. So this peroxide here has to be overall -2, which means the individual one is -1. And then the general form of a peroxide is like so. So again, 2 oxygens together with a single bond, and then it could have any other substituent, right? So that's what R means. And I think there are even like nitrogen-based peroxides and all sorts of peroxides. So there's really an unending list of peroxides. So again, just watch out for that O double bonded to another oxygen. All right, otherwise it's always, always, always -2 for, again, right, like determining the metal or something else. Oh, there's our rule of our elemental state is 0. Okay, but we remembered that. And again, doesn't matter if it's like S8, so weird allotrope, right, still 0. And so then in an ionic compound with 2 elements, the metal or the more electronegative atom, I think that's wrong or something. I think it's supposed to be the opposite way. Typo. So yeah, the more electronegative atom should have the -1, ideally. But that is a typo. Should have a negative oxidation number. And the metal, see, this is all wrong. So this is typically, right, our nonmetal. So typically your nonmetal should be more electronegative and be negative, again, typically speaking. And then our metal or less electronegative atom should have a positive oxidation number. Sorry. But again, that kind of makes sense, right? So that's, if you recall back to CO, right? That's kind of the funny thing about CO when we're trying to balance our formal charges even. And recall that that's a weird one since the negative charge is on the carbon, which is more positive. And then, so most of these track with what we expect, right? Our group 1 alkali metals. So like we saw in our demo, so again, right, they make compounds, oxidation state of +1. So ready to lose those electrons. Alkaline earth, group 2. So again, we remember those are 2+ typically. Calcium, magnesium, strontium. And then we have hydrogen. So again, hydrogen is typically +1. But then it is -1 when combined with the metals. So sodium hydride is one of those examples. Often you'll also find like aluminum hydride or any other like metal hydride. So sometimes there's like iron hydrides, but so in that case, hydrogen is -1. But again, only in our metal situation. And then halogens. So again, obviously fluorine is always -1. But then, of course, we find that our halogens are typically -1. Again, we know that, right? We've seen that, just kind of emphasizing that. Although we could find weird oxidation states, like I'm sure like I3 would have some weird oxidation states in there, so we'd have to go through that formally. Or the middle one, rather, would be positive. And then, of course, right, just balancing our charges is all this is kind of getting at. So like mercury, for instance. So this is kind of a strange case where we have this mercury 2+. So that means each mercury itself, though, is 1+ in that case. And then, I mean, you guys probably know this, but for the polyatomics then, right, our oxidation state of our individual atoms must equal the charge on the ion. And again, right, we're always assuming oxygen is -2. So we can go through that. So it's gone, they go through it here. So, right, going back to nitrate, so NO3, -1. And so, okay, oxygen is -2 typically, so -2 times 3 is -6. So that must make nitrogen +5, right, which isn't out of the question for nitrogen, right? So go back to your periodic table. Okay, well, nitrogen is either -3 or formally +5, right, if we go the other direction. 1, 2, 3, 4, 5, right, bringing us to helium there. And so you could write that as well for kind of the alternative oxidation states. But I think your periodic table, too, also has a few extras on there. All right, so then we can go back to this example and put numbers to this because I like seeing how many electrons are flowing. And so, okay, chlorine, what's the oxidation state? So 0, so good, right? Elemental form. So we go from 0, and then luckily this is pretty obvious. So what's this? Also matches with what we expect, right? So what's chlorine typically?
-1.
So -1, good. So we went from 0 to -1. And then, right, just now counting up our total equivalents. So, okay, that was 1 electron for each chlorine, but now there's 6 chlorines total. So again, just kind of sketching that out. So 6 electrons total. So we can see that. So that's also part of the process. Again, we said these redox reactions are coupled, but then that also means that the number of electrons should be the same. And so now looking at iodine to iodate here. So what does this start off as? So -1. So then we go from -1 and then, okay, base it off of this one. So oxygen, right, -2. So what do we find our iodine is? So +5, and then that does work out, right? So there's only 1 equivalence of iodine, and we go from -1 to +5, so that's also a 6 electron process there. So 6 electrons lost, and I should have put that we were gaining 6 electrons up here. And so again, that matches. And so with this one, I think it'll be more obvious like when we're doing metals, because there's a question about when we do it. But it'll be more for like when we have kind of 2 metals and then we'll like divide it, but we'll see more examples. All right, so let's start to look at our balancing. And so the balancing process is fairly tedious. And so students do have issues with this. I think, again, just because it's a long process. My biggest advice would be to give yourself plenty of scratch paper. So these problems just need space, and then I think it'll go okay. All right, so we'll kind of go through the rules, but then we'll go through a few examples together. All right, so first we're going to balance our redox reactions. So again, like I said, not only are we going to have to balance the atoms, but now we have to keep track of our electrons. And so that's why this half reaction method is used. And so like I said, we'll go through an example, but let's kind of walk through our steps here. So we're going to, again, find our 2 half reactions, our oxidation and reduction half reaction. And then we'll put our electrons on the appropriate side. So again, they're going to go on the product side of our oxidation. And then they go on the reactant side of our reduction. Then first we'll balance for atoms. Then we will compare our 2 half reactions, see what adjustments we need to make, right, so that we have the correct total number of electrons lost and gained so that they're equal. Like I said, this will make more sense once we go through it. And so then this is kind of the more detailed step. So yeah, this goes through everything in more detail. But like I said, we're going to do it together. So oxidation states, half reactions, and then this is where this can get a little tricky. So we'll balance our elements other than hydrogen and oxygen. And then we'll look at two different cases. So we'll start with the acidic condition. And so for the acidic condition, we'll first balance our oxygens with water, and then we'll just add H plus as needed. And then if we're not in acidic conditions, then you'll go on to formally neutralize your H plus with hydroxide. So adding hydroxide to both sides. But like I said, we'll go through all this together. And again, same thing, balance for electrons, compare, add. But let's do that. All right, so we'll start with this simple one. And so now we're looking at this reaction of aluminum metal and copper 2 plus. So it looks like it's going to aluminum 3 plus, right? And then copper elemental form. So then we just want to separate out our reactions. So that's at least easy enough in this case. So then I like to make two separate columns. So I'll have what's reduced on one side. So reduction is gaining electrons, so that's going to be my copper. So it's going to go copper 2 plus to, of course, the elemental form. So how many electrons is it gaining? So 2, so plus 2 electrons, and gives us our copper metal. All right, so that's 1/2 reaction. And now let's do our oxidized. And so how many electrons were lost here? So 3, excellent. All right, so that's our half reaction so far. And then pretty simple, right? Like I said, we're starting off easy. So balance atoms. Well, okay, everything's already balanced, right? Now we need to balance electrons. So how do we balance our electrons, right? We have 2 on one side, 3 on the other.
Multiplied by the LCD.
So multiply. So I'll multiply this side by 3, right? So 3 coppers plus 6 electrons gives us 3 copper. And then good, same thing on our oxidized side. So now this is times 2. So 2 aluminums give us 2 aluminum 3 plus 6 electrons, good. And so again, just kind of double check yourself. Okay, this is looking great. And so now we can add our half reactions. And our electrons, of course, can cancel out. So anything that's on the reactant and product side can, of course, cancel. So good. And then we can just, again, kind of rewrite this reaction. So 2 equivalents of aluminum plus 3 of our copper 2 plus give us 3 equivalents of copper and 2 equivalents of aluminum 3 plus. So see if you can play around with this one. Of course, it is in acidic solution, but at least see how far you get. So remember, for acidic, what we'll do is we'll balance any extra oxygens, which I don't see any oxygens, but balance any extra oxygen with water first, and then we can add just H plus at the end. I'll give you guys a few minutes to just play with it first. So who's getting oxidized, who's getting reduced in this one? Hydrogen is, yeah, so hydrogen is getting reduced. So going from 1 plus to 0. So gaining electrons here. And we'll balance it out, right? So I'll write 2H plus, since I have H2, so we need 2 plus. So then that's going to make that a 2 electron process, right? So since there's 2 equivalents, and so then that gives us H2 gas. So good. So again, elemental form. And so then that must mean that our chromium is oxidized. So chromium, and then going to the 2 plus oxidation state, so 0 to 2 plus. And so it looks like the electrons balance out in that one. And then we really didn't need to do anything else, right? Balanced out our atoms, the electrons were already balanced. So now we can just go ahead and add them together. So I'm just going to rewrite it for a second before crossing out our electrons and of course anything else, but in this case we didn't have anything else. And rewrite it. So 2 equivalents of hydrogen plus chromium give us our chromium 2 plus and our hydrogen gas there. Oops. Questions on that one? All right, let's try a little trickier one then. So just play with this one for a little bit. So again, you'll balance any extra oxygens with water. So you may need that for this one. And then add hydrogens and neutralize the hydrogens. Wait, just see how far you get with these. All right, let's kind of see how we're doing on this one. So again, we'll separate our reactions. So you guys can tell me what you did. So it looks like, right, iodine is going from -1 to 0. So it looks like that's getting reduced. What's our manganese oxidation state? So what's it in this compound? Yeah, so +7. So again, basing it off of oxygen, so good. So -2 times 4, so -8. Then we need -1, so that's how you got 7 plus. And then what's our manganese in this compound? So I see a 4. And so again, looks like our manganese is losing electrons there. All right, so let's separate that out. And so again, I'll balance this by adding a 2 here. And so then that takes our -1 to 0. So right, 1 electron process, but then 2 of them, so 2 electrons. And let's look at our reduction half reaction. And 3 electron process, right, from 7 to 4. So plus 3 electrons gives us MnO2. All right, so then do we all at least make it to the first step? And then, right, balancing out atoms, at least ignoring oxygen and hydrogen. And so now this is the step where we can say, okay, add H2O to balance our extra oxygens, right? So then we need 2 equivalents of water on our product side. And so now that I threw in a bunch of hydrogens, well, now I have to fix that. So now I'm going to add H plus to balance. Oops, sorry.
Didn't it say basic solution?
It did, but remember, so first you have to add the hydrogens and then you neutralize it. So that's what's kind of confusing and messy. So yeah, so first, so we still aren't finished. Okay, we need 4 hydrogens to balance it out. So now we're here, but then, yeah, like you'd said, okay, we are in basic solution. You definitely, right, when you're looking at these problems, definitely star that, whatever you need to do, so that you remember to keep going. So now we need to balance for basic and neutralize. So we're neutralizing our H plus with hydroxide, but whatever we do to one side, right, we need to add to the other. So we'll add 4 equivalents to neutralize this H plus, but then that also means we need 4 equivalents of hydroxide on the product side. So I'll do plus 4 hydroxide, plus 4 hydroxide to show that. And so now let's see where we're at. So this is where these problems can get, right, a little lengthy. So I'm like, give yourself some paper. And then, so now plus 4 water gives us MnO2 plus 2 equivalents of water plus 4 equivalents of hydroxide. Again, now accounting for our basic solution. So that looks good. And then before we get to the electrons, let's take care of our water, right? Because we have 4 and 2 here, so I'm going to get rid of this. And then this becomes 2 equivalents of water. All right, does that look good there? I'm just kind of double checking everything. And so now we need to add our half reactions and balance for electrons, right? So I'll zoom out so we can see. So similar situation, right? We have 2, we have 3 electrons, so least common multiple gives us 6 again. So we'll multiply this equation by 3. So coming to the end here, do we have questions? Sorry, I should make sure. Do we all get to kind of this point or at least see it? All right, I just don't want to move too fast. And then, so now last bit, just balancing our electrons. So I'll say balance electrons and add. So again, this is times 3 times 2. And again, you can certainly see why you need a lot of scratch paper for these problems. So now I'm just trying to write the individual ones. So 6 equivalents of iodine gives us, or excuse me, iodide gives us 3 equivalents of iodine here. Plus 6 electrons. And then multiply this times 2 plus 2 equivalents of this manganese oxide plus 6 electrons plus 4 water gives us 2 MnO2 plus 8 hydroxide. And so again, getting rid of electrons at this point, right? If we had any other extra water hanging around, we would eliminate that. And I'll just rewrite it. So just taking everything on the reactant side. And everything on the product. Oh. All right, do we all get to there? So now's probably a good time for a break anyway. So I'll take a 10-minute break. I'll kind of leave this up here so you can stare at it if you need to. And then we'll practice another one. Because, again, it's a little tedious, right? But if you just slow yourself down, write it out, give yourself space, I think you'll be okay. We'll take a break. Oh, there's still some stragglers from break, I guess. Did any questions come up on the last one? Any thoughts or anything? So let's just start another practice, especially while people still trickle in. So again, same sort of thing, another basic solution one to keep us on our toes. So just start trying to work through this one now. Yeah, that's C.
L, right?
Yeah, I think it's supposed to be CLO.
Okay. I was like, well, where's the I on the product side?
Yeah, I think that actually is like a weird typo. It does not look correct. But yeah, while we're looking at this, let's just go over our oxidation states before we get too deep. So then looking at this hypochlorite ion, ClO here, what's our oxidation state of chlorine then? Again, basing it off of this assumption of oxygen being -2, right? So +1, good. And then, okay, so it goes from +1 to, well, what's this one, obviously? So -1, so it looks like a 2-electron process there. And then, so let's look at chromate in this chromate hydroxide species. So again, we can take all our hydroxide as -1. So -1 times 4, so then what does that leave chromate? +3. And then if anybody needs more polyatomic sheets, let me know. I just printed out a bunch for my Chem 104 class, so I should have like extras floating around if we needed new polyatomics to remind ourselves. I might have other special cheat sheets for y'all, but I'll look. And then what does it go to? And this last one, in this chromate over here. Plus what? +6 there, good. All right, so I'll let you play with it for a little bit longer, seeing how far you can get at balancing in basic solutions. How are we doing on this one? So just kind of looking at our chromium side first. All right, I wrote it out, our half reaction there. And then, okay, everything balanced, right, with our elements pretty nicely, except we had these extra hydrogens, right, so balance with H plus first. But then we said, okay, well, we're in basic solution, so we have to add 4 hydroxides to each side. So I'm looking something like this. And let me know if you have questions or got lost somewhere. So that was this side, right, before combining. Just kind of pause there. And then this side, right, we probably had to add water to balance out this oxygen. So I'll just sketch out what I did here. So right, 1 equivalent of water, but then we needed to add hydrogen, right, to balance that. But then again, we said we're in basic conditions, so we need to Add our hydroxide on both sides to get rid of this, so neutralize that. So 2H2O plus ClO plus 2 electrons gives us chloride plus water plus 2 equivalents of hydroxide. And so then we can cross out the water at least, so get rid of 1 equivalent, and now we're down to 1 on that side. So does that look okay? Did we all get to this point? Okay, I'll slow, or I'll let people write that out for a second. No questions about any step though? So then once we make it to here, right, it's just balancing our electrons at the end, so least common multiple, so that gives us 6. So we should take this side, right, times 3, and our right side times 2 here. So I'll start kind of writing it out. Again, these things get kind of tedious and somewhat messy. And as always, just double check me. Oopsie, 6 hydroxide there. So I'm just rewriting it before I smash it together. So now 2 chromium. All right, so now we should have something that looks like this, right? And now we have to start eliminating what's the same on the reactants and product side. So I'll start with the electrons. That's kind of easy. And so let's see, what else do we have? So we have 6 hydroxides on this side, 8 on the other. So I'll get rid of these. So that leaves us with 2 hydroxides. Then waters, so this can go away, leaving us with 5 waters. So I think that's everybody. And so I'll just rewrite it one more time of the final reaction. So 2 equivalents of our chromium hydroxide species plus 3 of our ClO plus 2 equivalents of hydroxide give us 3 chloride plus 5 water and 2 of our chromate there at the end. So do we all get to that point? Or still kind of working on it at least? Do we feel okay about half reactions, balancing half reactions for now? So let's look at some other practice problems. I'm going to make a new section here. So before we get into like the eChem, because the eChem admittedly is like kind of more next chapter, let's spend some more time on our oxidation state practice. And so this will kind of go back to the question that was asked earlier, but then this is good practice for us for two different reasons. And so I believe this is in your homework. And if I remember correctly, it's just like, oh, determine the oxidation state. And so we're going to look at this example. And so it's given as Fe3O4 minus. And so it wants the oxidation state. But then I'll kind of reveal something once we establish kind of what the issue could be. Well, I thought there was just like a determining. I have to look at your homework.
Oh, I see it. It's in the second column.
Right. Oh yeah, it's over there in the front page on 3. All right, so let's go through this one mathematically together. So what would the answer be, right? So we have this compound, overall -2, so we base it off of oxygen here.
Nice question. I'm hoping it doesn't have the 2 negative superscripts.
Oh, that could be my bad. Yeah, maybe we don't need to. It actually makes it easier. So what's its oxidation state? So sorry for the... So yeah, just this one, Fe3O4, no charge, sorry for that. So what's the oxidation state?
You have -8 from the oxygen. How do you get that ion to oxidate?
Yeah, so that's the problem, right? And you could kind of do this average oxidation state. So we're getting at what we have. So oxygen, right, there's 4 of them, -2. So we have -8 plus 3 times x is equal to 0, right? Just kind of setting up the algebra. And so then we get something, if we solve for this, of course, that x equals 8/3, right? And so there's kind of a few different ways to look at it. This is like, yes, this could be our answer of 8/3, but let's talk about what this means, right? Because what this really is, and why, or at least it should trouble you, is, huh? So not resonance, but close. It's just, we have mixed oxidation states, right? And so the problem with this is you're not given a structure at all. And so I will reveal the structure, and if I reveal the structure, you could probably figure out who's who. So again, right, this is just our average oxidation state. And so again, right, like this is not a wrong answer, is what we're saying. Again, it's the average. And this is about all we can know. But if I were to give you the structure, so now let me draw it out for you what this actually is. And so these are 3 bonds going to iron. And so again, now we're trying to still get to positive 8 total. You could start to slowly become inorganic chemists now. And so you want to just kind of see how many electrons are involved in bonding is typically how it works. And so, right, we have oxygen here. We could draw out, right, it's lone pairs. That's still fine. It still has all these lone pairs. And so that means that each one of these oxygens, right, is contributing 1 electron in this bond. Well, that means that this iron then is contributing how many electrons? Yeah. So it would be 2, right? So again, they're each contributing 1. You could back out this Lewis dot structure if this helps you, right? So it's making our bond with these. And so, okay, yes, iron is contributing 1 electron to each one of those bonds. So that makes it iron 2+ then. So now you're starting to learn how to be an inorganic chemist. And so what about these irons? So they have 1, 2, 3 bonds. So what can you guess that its oxidation state is probably?
3+.
3+, good. And so, okay, we add that up, 3 + 3 + 2. So that does give us positive 8. So again, right, you can see how the structure tells you how it's actually, right, that we have 2 that are 3 and 1 of 2. But again, for the purposes of your homework, 8/3 is just a perfectly fine, acceptable answer. But again, just know that that's your average oxidation state, right? It's not telling you the true details. But again, we need a structure, so you really couldn't figure out this answer. All right, so let's try some other shapes. So now let's look at this compound. So this vanadium oxide chloride, trichloride species. So just determine the oxidation state of vanadium. So what do we get for vanadium, right? Balance it out. What's oxygen typically?
-2.
And then our chlorides are,
Well, the vanadium is +5 and the chlorine is -1, right?
yeah, so base it off of the oxygen and chlorine though. But yeah, so then we should get vanadium +5. And again, we can just start to think like an inorganic chemist, drawing out our structure. So there's, again, our 2 electrons involved in bonding on vanadium, right, to oxygen. And then our 3 chlorines. So again, just thinking back to your Lewis dot structure of chlorine, and it has 7 dots, one of those prime for bonding. So again, vanadium has to contribute an electron there. All right, let's try another metal one. So let's look at this titanium hexafluoride compound that has a 2- charge on it. So what's titanium's oxidation state? So what do we get for titanium's oxidation state?
On average, it's 3/2, right? If you do the math for it.
Well, there's only one of them though, right?
And then it's just 4 plus.
Yep. So 4 plus for titanium, and then just drawing out the structure so we can see that it again has 1, 2, 3, 4 involved in bonding, and then 2 minus. So extra electrons again helping to contribute to that bond there. All right, let's try a little trickier elements here. So now we're going to look at organic compounds. And so typically to find the oxidation state, what we do is you pull off your atoms, so like separating them, and you give your electrons to the most electronegative. So starting with just simple methane to practice, so it looks like this, right? And so carbon is slightly more electronegative. So now we're going to pull off all the atoms such that carbon gets all 8 of them. So then that leaves kind of 4 naked hydrogens, and then this carbon here. And then we could take our formal charge, and so we just take our electrons in our neutral compared to this. So of course 1 minus 0, so all these hydrogens have a 1 plus oxidation state. And then the carbon, so you have 1, 2, 3, 4, 5, 6, 7, 8. So 4 minus 8, so that gives us a -4 oxidation state for that one. Let's try another one. So let's just draw out. Oops, sorry. Whoa, crazy. What am I doing there? All right, so first I'm going to draw it like this. But then you might want to redraw this in a form that doesn't look like just a skeletal structure. So translate this, so CH3, right, that's a methyl group here. Here's another carbon. And then again we need 4 bonds, so 2 hydrogens there. carbon double bond to our terminal carbon there. So hydrogen, hydrogen, and then fill in. Right, there we go. And well, let's actually do this one together. And so part of the trick though, so let's just say we have a carbon-carbon, right? So I said pull them off so that the most electronegative gets them. But if you have two of the same, you can just split them apart. And so now you want to kind of practice doing that of pulling off. So pull it off. So split those evenly. So now we can kind of start piece by piece. And so this is also one of those processes, right, that gets a little repetitive, which is good. So this bond was split evenly, but then it gets all these electrons. And so hydrogens, right, again, we can usually assume they're 1+ oxidation state, which match there, yeah.
So it's taking an electron from the other carbon too?
So I said split those in half then, if they're the same.
7 on it then?
Yeah.
Okay.
So then going with 7, so 7 minus 4, so what's the oxidation state of this? Or sorry, 4 minus 7 is how we should do it. So 4 should be the neutral, minus 7, so what's our oxidation state on carbon? So -3. And again, this should kind of make sense because with organic compounds, they tend to kind of cancel out right next to each other. So, okay, we have -3 balanced out with this +1 times 3. Okay, so that's still neutral. And then, so going to this carbon, we can do the same thing. Again, it only gets 1 from each of these bonds, but then it gets both from the hydrogen. So each hydrogen is 1+ again. So what's my oxidation state of this carbon?
-2.
Good, so -2, and again that balances with our hydrogens, so carbons don't matter. All right, so let's look at this one. So again, it just gets 1 from this one, and then 4 electrons, split those in half, so it gets 2 total from this double bond there. But then it gets 2 from the hydrogen. All right, so what's my oxidation state of this carbon? So -1, good. Hydrogen's still +1. And then last carbon, so you could probably mentally do this one, but I'll pull it off. So again, it gets 2 electrons from the hydrogen, 1 from each one of these double bonds. So hydrogen's 1+. Then what does that leave this carbon as? -2. Good. And so again, this is the proper way, right, to do our organic structures. If we had just been given a formula, so let's go through this. 1, 2, 3, 4. So C4H 1, 2, 3, 4, 5, 6, 7, 8. So right, if we just kind of did this formally, every carbon, so what's our average oxidation state of carbon here? Base it off of hydrogen, right, being 1+. What's our average for carbon? So 2, so it should be -2, right? But again, this is just to point out that this is an average oxidation state, and we need the true structure, right, to again determine, well, this one was -1, this one was -3, and yeah, these were -2. So it did indeed average to -2, but again, we need the structure to really get it. All right, let's try another practice. So we'll go back to kind of a simpler-ish one. So take a few minutes with this one, see if you can determine the oxidation states, and then we'll go over it. So I'll kind of start sketching it out, right? So we have our carbon in the center, then we have to pull all our electrons to the more electronegative one. So oxygen is going to end up with all of those. So we have carbon here in the center. Okay, so it lost that battle, but then it's also going to lose to this oxygen, right? So it doesn't get anything from this bond. So I'll make my hydroxide over here. So again, okay, that stole everything, which makes sense, right? So that gives us our -1 for hydroxide that we expect. And then, so carbon-carbon, so at least they split this one evenly. So it just has one electron right after the split. So what's our oxidation state for this one? Yeah, for the center one. Yep, so +3, and then oxygen, what does it work out to, which is again what we expect by definition, but it does match. So 6 minus 8. So what does that give us for oxygen's oxidation state? So -2, but again, right, we kind of expected that. So then just continuing to pull things off. So we could go back to this hydroxide. So again, we could formally prove this. So of course oxygen would also take this bond. And so now we have the -2 comes out again, right? 6 minus 8 there. Hydrogen's left with nothing, so there's 1 plus. But again, we kind of expected that, right, from hydroxide. And then we have our little methyl group over here. So we got 1 from this bond, and then does get everything from the hydrogens. So what oxidation state is this carbon?
-3.
So -3. And then that leaves our hydrogens all as 1 plus. And again, I just think that it's funny because our carbons could average to an oxidation state of 0. So again, if you're calculating this more mathematically, you might get 0 for carbon's oxidation state, but that's where, again, the structure is important. All right, let's try. We'll do an easy one again, and then we'll end with kind of a larger organic.
How do you, is that acetic acid up there? Like the solution?
It is acetic acid.
How do you write it out where like C is equal to, so it's 0? You just, like one's -3, one's +3, so now the,
Well, if you were to average this, so let's take it, so C2, H4O2, right? And so just looking at this, well, right now they're already balanced, right? So hydrogen, if it's typically 1 plus, so 1 times 4, so that gives us +4 right here. And then -2 times 2, so that's -4, right? So that's already balanced, right? So then you might assume just from this formula that carbon is 0, right, for the oxidation state, but you can't tell, again, without the structure that, oh, one's actually +3 and the other is -3.
but like on the horn, would you want to be equal to 0 then?
I see. There is acetic acid there. Either way, because again, you don't have the structure, so you don't really know. I mean, you could kind of piece together. So I would accept either answer on that, of either an average of 0 or kind of from the structure, you know. Because, yeah, like I said, from your homework, it really doesn't give you the structure. But on the exam, I'm going to test you with the structure so that it's not, like, super ambiguous. So let's try, we'll do an easier example, maybe. All right, so try this one, and I'll put the lone pairs on there. Oh, and this should have a negative charge on it overall. All right, what do we get for our oxidation state? So pull everything off. Carbon loses to sulfur and nitrogen. So what's sulfur's oxidation state here? Yeah, -2. And then what is carbon left as? Not 0, but because it should have 4 normally. +4. Yeah, because it's 4, so what it should have, valence electrons minus how many it has, so 4 minus 0, so +4. And then so nitrogen ended up with 8, so it should be 5 minus 8. So what does that give us for the oxidation state? So -3, and then just again double check since it has a -3 charge, so that does check out. All right, I'll draw a nice organic structure, and then I don't know if we'll have time to go over it. At the very least, you can look at it, and then we can pull it apart on Thursday. Now I forgot what drug this is, but so sorry, give me a second to draw it all out. So this is an aromatic ring of benzene.
Oh my goodness.
And then, so yeah, we may, like I said, we may say this for Thursday then. Okay, I think I attached everything on there. So at the very least, kind of copy this down, and then you can chew on it between now and class. See if you can do it on your own, or like I said, we'll probably just go over it on Thursday so that people have some time to spend with it. So I think we're out of time. So again, we can just end here, copy it down, and then again, just ask me questions, especially if you're having trouble with the balancing solutions, so we can practice that some more on Thursday too if people need. But yeah, we'll start off with this. So try to go home and determine the oxidation states if you can on this organic compound. Otherwise, ask me questions, and I'll see you in lab, so hopefully the lab goes well.